So I think I finished the part on the HDL code generation, on application-specific code generation for DSP and wireless communication. I will start with the HDL code verification. For that, we call the HDL verifier toolbox. I think I will visit 4 verification types that we provide. With that being said, we have some other verification types that that we provide also, but that are not listed here. But I will mainly focus on co-simulation, FPGA in the loop, and UVM. Okay. So what I like to say is to start is the presentation here is based on the fact that, okay, we have some MATLAB and Simulink model, we generate code, we are trying to leverage the fact that we created our test benches in Simulink and MATLAB in order to use that in co-simulation or FPGA in the loop. But what should be also known is that what we are, what I'm presenting here, it could be also true for handwritten code. So if you are someone who's more on the verification side, that you don't go through code generation, you can still use HDL verifier in order to verify your HDL code. So you will be writing your MATLAB or Simulink test benches. You will be also using MATLAB and Simulink to analyze the result of your HDL your HDL code. Okay, so just a small note to say that even if you do only MATLAB algorithm development and in MATLAB, and later on you prefer to still write your HDL code, just know that the test benches that you used during the validation of your algorithm could be used later on for your HDL code, right? So you can import your HDL code and use the same workflows that I'm showing here. So going to HDL verification, so of course you will have verified your models in MATLAB and Simulink, but as you keep going towards the hardware, you need to add more verification, but this time it will be on the HDL part. And one of the ideas that you could have is to co-simulate your generated RTL code with your MATLAB and Simulink test benches before the hardware team integrates this HDL code directly on the hardware. So this allows a visibility into both sides. So the MATLAB and Simulink side and the RTL or HDL code side, right? Another way to validate our HDL code is using the FPGA in the loop workflow, where you can this time use your test benches of MATLAB and Simulink in order to test your hardware directly, your code directly deployed on hardware, right? So, and one of the last application, I'm going here a little bit fast, but I will go through in details to each presentation of our verifications. So we can also generate some system verilog DPIC for that we can provide for the verification team that can use this system verilog DPIC to generate test benches for the reference that will be in, of course, system verilog DPIC, and to provide the same test benches for the DUT, and later on compare the results outside of the environment of MATLAB and Simulink, in order to compare the result between the reference and the DUT or the RTL design. So we'll go through the co-simulation of FPGA in the loop and the UVM later on in details. Let's start with the co-simulation. So the idea behind it is to use a third-party HDL simulator, where we can, like I said, we can use the HDL MATLAB and Simulink test benches. We are gonna use the algorithm in order to simulate the Simulink model, and in the same time simulate your HDL code in your RTL simulation. So the HDL code execution is not done in Simulink and MATLAB, but rather in the third-party HDL simulator. And what Simulink will or MATLAB will do later on is to reuse the data that is coming from the third-party HDL simulator in order to compare it to what you have in Simulink, to the result that you have in Simulink, and to analyze the differences, of course, between your Simulink model and your HDL code. So, like I said, you can have we are very flexible on the HDL resources or sources. We could have some handwritten or auto-generated code. This actually, this is a screenshot. This one is a screenshot from Model Sim or Questa Sim, and you will, of course, you will be having your waveforms in your simulator, but also you will be having a comparison between the COSM and the DUTRF in Simulink, where you can the error is computed directly between the results in co-simulation and the HDL code execution. We can also have some coverage analysis in MATLAB and the HDL simulator, right? So what you see here is what you could have for model coverage, and what you could see here is what you could have in Questa Sim for code coverage. Today we have a support for 3 RTL simulator: Siemens for Questa, Cadence, the RTL simulator of Cadence, and the simulator of Vivado. So you can have this bridge between what you have in Simulink and what you have in your HDL code directly using these 3 tools. Another way of verifying your HDL source, of course, is FPGA in the loop. So it's very similar to what we have in Simulink, in co-simulation. You will be using the same MATLAB and Simulink test benches, but this time the code execution will not be in a third-party tool, but rather it will be directly on the FPGA, right? So, and we have a structure that is implemented directly also on the FPGA that will be responsible on synchronization between Simulink or MATLAB and your FPGA. Okay, and of course you can achieve this the link between the FPGA and Simulink through Ethernet, JTAG, and PCI Express. So for that also you will be needing a hardware support package that we can provide freely on the on our with our tools, and we usually support the development boards that are very used on the market today. The third way of verifying our HDL source code is, and actually this solution is because a lot of our clients wanted to also validate their HDL source code outside of MathWorks tools and MathWorks environment. So what we can also provide is creating a HDL test bench this time. So you will not be using, once this workflow is complete, you will not be using Simulink and MATLAB. You will be having an HDL test bench that is equivalent to what you have as a test bench in Simulink and MATLAB, and you will be able to run this HDL test bench that will be calling, of course, your HDL code, and you will be having a standalone simulation this time using your HDL simulator. So in that case, you are not dependent on your RTL simulator. You are just creating a portable HDL test bench and portable HDL code, and you have a self-contained test bench. So it will be calling the DUT, the input stimuli, and you will be having a pass-fail at the end of the simulation where the results will be compared to the expected results that you provided in Simulink. So it's all in all, it's a self-checking test bench that you can either have it for cross verification and testing if you want to have another level or a way of testing your code, or you can provide to someone who is not familiar with MathWorks tools or don't have access to MathWorks tools. So you have your HDL test bench in a standalone mode. A very popular way of for RTL verification, specifically for ASIC designers or ASIC design verification engineers, is UVM, or Universal Verification Methodology, where you can use what you did in MATLAB and Simulink as for test, for system environment, for results analysis, and of course your design under test algorithm, in order to create the UVM verification environment, right? So you'll be having your sequencer, your driver, your virtual interface and monitor, and later on you can also ask, you have some like you can even add some predictor if you have provided that in MATLAB and Simulink. So in that case, what you will be doing, you will be having all the test management, the coverage, and the requirement tracking in MATLAB and Simulink. And with HDL verifier, it will ease the transition between the MATLAB and Simulink environment and having, of course, a VM verification environment. And it goes without saying, actually, what we are generating in this part here with the UVM verification environment is a standalone environment. So you can go and use it to run it, for example, in QuestaSim without the need to use or to call MATLAB and Simulink tools during the simulation. Actually, I like I said, I chose these four verification types that we have. You can go and explore some other of our solutions, like FPGA data capture, where you can capture some. Where you can capture a lot of like data and buffer some data on your FPGA. We have some other solution like MATLAB Aximaster, where you can write and read some data directly in the registers. But I prefer to stick to these four verification methods. But if you have any questions, of course, you can put them in the chat and I will answer them later.